How can we travel to distant galaxies or forward and backward in time? For years, scientists have sought answers to these questions, and in 1935, Albert Einstein and Nathan Rosen came up with a possible answer: the Einstein-Rosen bridge, more commonly known as the wormhole. What exactly is a wormhole? Well, it's a topological feature of space-time which acts as a bridge between two separate points in space and time. The basic idea behind a wormhole is Einstein's theory of relativity, which says that the fabric of space-time can be warped and bent by the presence of energy and mass. Because it's really hard to imagine how three-dimensional space can be bent, let's take a look at the relationships between some simpler spatial dimensions. One-dimensional space has one dimension, length. Two-dimensional space has two dimensions, length and height. Three-dimensional space has length, height, and depth. Four-dimensional space is extremely hard to visualize because, well, it has four dimensions. So, we were talking about how three-dimensional space bends according to general relativity. It's easy to imagine how one- and two-dimensional space bend because we can see them from an outside perspective. But to see three-dimensional space bend, we would have to have a four-dimensional perspective, which is really, really hard to imagine. So we'll start our study of wormholes by studying two-dimensional wormholes. This is a two-dimensional universe. A person in this two-dimensional universe won't notice if the two-dimensional universe is bent, but we, from our outside perspective, can see that the universe is bent. Now for what we've been waiting for. This is a wormhole. It forms a bridge between these two distant parts of space, making a shortcut. Just as wormholes can connect different points in space, wormholes could also connect different points in time. Another concept of relativity is time dilation. An accelerating system experiences time at a slower rate than a non-accelerating system. The greater the difference in acceleration, the greater the difference in time. So an object with a low acceleration will be farther ahead in time when compared to an object with an extremely high acceleration. So how can we use wormholes to time travel? A wormhole has two ends. If one end of the wormhole is accelerated to an extremely high speed, and the other end of the wormhole remains stationary, then the accelerated end will be much farther behind in time than the unaccelerated end. An object that travels from the unaccelerated end of the wormhole to the accelerated end has traveled backward in time, and an object that travels from the accelerated end to the unaccelerated end has traveled forward in time. Now that we have a pretty good idea of how a two-dimensional wormhole works, we can also have a pretty good idea of how a three-dimensional wormhole could work. A two-dimensional wormhole is circular. So, a three-dimensional wormhole would be the three-dimensional equivalent to the circle, which is the sphere. So a three-dimensional wormhole would be spherical. This is the kind of wormhole that we could use to travel to distant planets, or even to the future. So, want to travel to a distant galaxy? Maybe go back in time? All you gotta do is find a wormhole and hop right in, right? Well, it's not quite that simple. You see, scientists have never actually observed a wormhole. In fact, they have some pretty good evidence that wormholes couldn't exist at all. Like, how can wormholes making time travel possible be consistent with the laws of conservation of energy? Or how can wormholes form without the presence of exotic matter or negative energy? Unless we can find positive answers to these questions, it's quite possible that wormholes will remain simply as an element of science fiction.